And we should be recording. Lab 3 will be put into 2 parts. This week will be part 1. It will be worth 20 points. It will be about constant acceleration. Next week's Lab 3, part 2, will be on free fall acceleration, which has to do with, put it in chat. What do you think it deals with? Let me put the chat up in my screen. What is free fall? What is free fall acceleration? What do you think it has to do with? What is free fall acceleration? Even though this is next week's topic. Did someone try to say something? I couldn't hear you. Okay. It's on gravity, but we won't get to gravity until next week. But I love gravity. It's cool. It's a force. It's weird. It's gonna be weird. Okay. Alrighty. Let's move on. Oh, this week's theme is the Grand Tour. It's gonna be a really short lecture, hopefully, so you guys can get on with your day. And so I can get coffee as well. Okay, acceleration. Who in here watches sports? Any sport? Any sport. Could be esports. That's also included. Anybody? Just type in me in the chat. Can you put emojis? I don't think you can. No, darn. And what sport do you play? If you play a sport. If you play a sport. Oh yeah, I guess I didn't say what sport do you play. Well, what sport do you watch if you watch sport? Nice. US Open for what? Golf?
It's tennis.
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 Nice. Okay, cool. Tennis, gotcha. Volleyball, sweet. Anybody else? Who doesn't watch sports? Who doesn't play sports? Okay. Basketball? Awesome. All right, these are all great examples because you can accelerate in every single one of these sports. Even rock climbing. You can start out at the bottom of the rock wall, like on the floor, and then you can climb and you can get faster and faster and faster and faster and faster and faster until you hit the top, and then you accelerate back down, or lack thereof. Cool, yes. US Open tennis. Oh yeah, heck yeah. You can smash the ball slow. You can like nail it across the court. I think that's what it's called, the court, I think. Yeah, everything, all these things accelerate. Volleyballs, you can spike them across the net. Absolutely, that's super acceleration. Basketball, obviously acceleration. There's acceleration going on. Very hard to keep a constant velocity with basketball. It's either super decelerating or super accelerating. You could dribble the ball. I guess that's kind of like constant velocity. We'll get there. We'll get there. So I have this link at the bottom. It's for Physics Classroom. It's lesson 1 about acceleration. We can go ahead and go there, although I already have it up right here. So this is a page. If you're having trouble with acceleration and you're not quite grasping things about acceleration, it's a difficult concept. I mean, I struggled with it when I was in high school. It was a little easier in college for me, but it's a difficult concept, even in fundamentals of physics. It's hard. So, but this website is really nice. It's really easy. They give you cool animations about stuff. Looks like the blue one. Yeah, which cars were undergoing an acceleration? Huh. Which ones do you think? Which do you think? What car? Which one of these cars was undergoing acceleration? Go ahead and type it in chat if you'd like. Go ahead and watch it a couple times. Okay. Anybody else? 5. Okay. All right, so we had the top and bottom cars, which were the red and blue ones. We had all of them, question mark, and we had red and blue, which are the top and bottom. So let's cut this apart. Let's slice this up. Were they all moving at the beginning of the animation? Were they moving? All of them at the instant it reset, this GIF reset. Were they all moving? Were they? At the instant this GIF reset, right now, are they all moving? Okay, no, they were at 0 meters per second, 0 meters per second squared, 0, 0, 0, 0, 0 across the board. Sure, 0 times. Yeah. I would say all of them are accelerating, because even though the green one, he's accelerating up to a certain point and then he just kind of stays there at a what? Type it in chat. What was the green car doing? Was it negative acceleration? Was it positive acceleration? Was it increasing velocity? Was it a constant velocity? Was it negative velocity? Yeah, the green car was a constant velocity. Heck yeah. Up to it, so it was after that certain point of getting started, it then went into constant velocity. You had a problem on this on your homework. Yeah, so this guy was, if this were the velocity versus time graph, you started out like this, and then it was a constant velocity just straight across. But there was this angle right here where he started at 0, went up, and then stayed at a constant velocity. Cool, okay. Which car is accelerating the fastest? You can shout it out or type it or whatever. Yep. Yep, the blue one, of course, yeah. Easily see that. Sure. Would you say, what's happening to the red car as time goes on until it stops and like resets? What's going on in that during that time? Okay. Cool. Anybody else? Yeah, good words. Good words. Anybody else want to type it in? Okay. All right. Nobody else. All right. Yeah, so there's something weird going on. He starts out from 0 and is first place, like right off the dot. Then all of a sudden he just like starts to get, and then the green car is catching up because we already know that the green car is going at a constant velocity. Now you're starting to see that this red car is like, what's going on here? Yeah, exactly, negative acceleration. This red car is experiencing negative acceleration as he begins to slow down. That's negative acceleration. Awesome. You guys have this. This is good. Sure. Okay, so what I was getting at with the sports stuff, was if you've ever watched sports, let's say football, and they're talking about, oh, he accelerated that ball so fast and blah, blah, blah. And I don't know, Antonio Brown caught it. Ooh, because I'm a Steelers fan. I'm from Pittsburgh. So you hear this person, the sports announcer, if you watch football, he's like, sure. Yeah, but is the ball actually accelerating through the air? For a little bit, but then it goes, so it accelerates, sure, up to a certain point. Just like the green car, yeah, pretty much. Then it starts to just have the same speed until it starts falling. Sure, we could kind of say that. Let's just say in general. Or you could say, let's say another thing, a person running down a field in soccer. The soccer person's like, oh yeah, the announcer's like, oh, look at that guy just accelerating down the field. You know, is he actually accelerating? Is this guy just accelerate, or does the announcer just mean he's going fast? What do you think? Sometimes not. Sometimes it just means that he's just going fast, this soccer player or she. You can be moving fast without necessarily accelerating, you know? Doesn't necessarily, you can be going fast, but you can be going at a constant velocity. Still going very fast, but at a constant pace without accelerating. You're not speeding up as time goes on. Acceleration has nothing to do with how fast you're going. I mean, you could watch my fingers here and you can just faster and faster and faster and faster and faster and faster. Yeah, or you can watch a snail. I have a lot of snails on my sidewalk out in the front of my house, and they leave slime crap all over my sidewalk. It's lovely. And because I live underneath a big tree, and I mean, they go super slow, you know, but they can be accelerating, or they can just be going into constant velocity. It's, you know, kind of however, but it has nothing to do with how fast an object is going. It has to do with the constant speeding up or the constant slowing down, right? Cool. We check that out. Yeah, so that's kind of what they're saying. Acceleration in sports doesn't necessarily mean that they're actually accelerating. This is a constant or a common misconception for sure. Okay, we'll get into the nitty gritty of this. In calculus-based physics, we would talk about instantaneous acceleration. However, that's dv over dt, and that's a derivative. That would be the derivative. So we're not going to get into that. We'll just say, which is kind of equivalent to, oh crap, I can't highlight stuff, to this. So this is kind of equivalent to this. Acceleration, or average acceleration, is delta v over delta t. Now, what does that delta mean? Does anybody know what that delta stands for? Can you type it in chat or? Exactly, and it's right over here that we can see acceleration equals change in velocity over the time it takes initial to final. The change in time as well. Yeah, final velocity minus initial velocity is over total time is acceleration. Sure. Okay, now we're gonna go ahead and read this, even though I know you all can read. This means that when an object going at a constant velocity, so like the green car was going at a constant velocity. If this car decided to change direction, like if he decided he was going the constant velocity, and then he's like, I need to go to the gas station, it's to the right or to the left. That change in direction, even though he's keeping that constant velocity, he changes direction. So now that's definitely affecting his movement. That's affecting his movement. So essentially that means he's accelerating. Now, if he's going at a constant velocity and he decides to brake, you know, just a little bit. You don't brake instantaneously. Like when you press on the brakes, you don't just instantaneously brake. Even if you slam on them, you still have that movement, right? I don't know how many of you have driven a car or have been in a car. I'm assuming every single one. You know that slamming on the brakes is different than just coming to a stop. However, there's no instantaneous stop. You're decelerating, negative accelerating. And by the looks of it, you guys already knew what that was. That acceleration is now in the negative direction. And we can think about this, we can determine negative and positive acceleration. I'm sorry? Is everything okay? Y'all good? Were you answering something? Okay, I'm gonna put him on mute. Okay, I don't think he was. Okay, so I think about it in terms of an XY plot. So we can write one. Let me go ahead and not screen share. Okay. Oh, that's horrible. Okay, that's really bad. That's not what an XY plot looks like. I'm sorry. Okay, straight line. This is not perfect, but it's a lot better than what it was. Okay, so this is an XY plot. What's the X direction going? Oh, well, we're mirrored. Okay, so let's see from your perspective. So this is clearly the X, right? It's going this way. And this is clearly the Y. It's going vertical. Cool. I hope you already knew that. If you didn't, you should. Yeah, so which way is the X going when it goes this way? And this is based on you because I know that this might be mirrored when it goes this way. So going this way. Okay, you weren't muted, but I muted you. It's okay. Okay, cool, awesome, thank you. I don't know whether you're being nice and like saying, but yes, this would be negative X, sure. Okay, what is this direction going? So this is the 0 point right here. This is 0, if you didn't know. Okay, what's this direction? Positive or negative? Yes. Positive Y. Cool. Okay, great. So we kind of know, I mean, opposite of positive is negative. All right, cool. So this is negative Y. Great. This is positive X, of course. Yeah. So I think of it, when I think of negative acceleration, I think of this person was driving at a constant velocity, like the green car was driving at a constant velocity, blah, blah, blah. All of a sudden, he doesn't slam on his brakes, but he starts to brake for whatever reason. Maybe he sees like a guy in the street dawdling, I don't know, whatever, selling candy, I don't know, being weird. Okay, so he sees this dude and he's pretty far away, so he starts to just press on his brakes. What direction would acceleration be going when he just starts to press on his brakes? Yeah, I like, yeah, exactly, negative, but I like how you said opposite, because technically, well, I mean, if you slam on your brakes, that would mean you're already going and accelerating. But yeah, technically, yeah, it would be the opposite direction of whatever direction you were going, sure. So he would be going this way. He would start to go like that, just a little. Well, I guess I shouldn't make it so big if I'm doing it based on scale. It would be going like that. Cool. Be going toward the negative. Okay. Let's say that the blue car saw the same guy in the street, but how fast? I mean, he was going pretty fast, right? Like he was like zooming out of there. So, and then he sees this guy, but that guy's, I mean, so this blue car is going really, really fast. And he sees this guy on the street, like holding balloons, and is like, oh my God, there's a guy, but I'm going so fast. Ah, like, what does he do? What does he do? In what direction would that be in? And what's the magnitude of the arrow, basically? What's that magnitude of the arrow? You can also say it if you'd like to. Anybody else? Or do you agree with what's in the chat? All right, cool. Okay, yeah, so this arrow from the blue car going super fast, all of a sudden he sees this weird guy on the street selling balloons, and he's like, ah, like, wow, what the heck? Ah. So his arrow is gonna be like really big. He's like, woo, like he's like put back in his seat. He slams on those brakes really, really hard because he's going really, really fast and doesn't have a lot of time to slam on those brakes. Versus the green car, who was just like da 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 lee 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 lee, and just like putting along, blah blah blah. And he's like, oh, okay, I'm just gonna like stop on his brakes and like come to a stop, and blah blah blah. Well, this blue car is like, nope. Exactly. Great job, you guys. You got it. Awesome. I'll stay there. Yes. Good job, everybody. Awesome, 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 awesome. Great. I'm gonna move you over to here. Great, so that's what this is. Yeah, so it's gonna kind of look like this. Make sure when you do your homework for this week, there's a part in your textbook that tells you what to do, how to calculate, how to do a physics problem, basically. And it's really good. It's very wordy, but I understand what it's saying. Of course, I already know what it's saying, but it's really good because in order to correctly write down a physics problem, you have to do a lot of things first before you can actually sit down and solve the problem. You can't sit down and be like, oh yeah, let me start solving this problem right now. Definitely not. There's a very structured step-by-step process you need to go through in order to solve a question that's asking, oh, what's the acceleration of this blue car? You know, and it gave you numbers. And I think, crap. I don't remember. I was reading the textbook though. Problem solving basics for one-dimensional kinematics. Problem solving steps. Okay, yes. Examine the situation to determine which physical principles are involved. So basically what we say is draw a free body diagram. Does anybody not know what a free body diagram is? And it's okay if you don't know, because it's a weird term. It's a little strange. Okay, a free body diagram is kind of like this, except it could be a chart, a X and Y axis, negative, positive, you know, whatever, like this. It could also be like this. I mean, it could be, here's your car, which I suck at drawing. It could be like that. And you could say acceleration is here, and this is V naught, or V, well, the initial, I guess I could just go by VI. Sorry, I'm so used to like V naught, which is the same thing as VI. And this would be T naught, which is just 0 seconds, and this is 0 meters per second, right? And then you could say, oh, VF is like right here. This is where the guy with the balloons are, and this weirdo that's holding these balloons. I can imagine being in like, I don't know where a weird guy with New York City, maybe? There's some weird people there. Yeah, so there's this guy right here holding these balloons, and this is clearly the final velocity, and this is T, I meant to write T final equals whatever. Yeah, so this is kind of like a free body diagram. And yeah, exactly. There's some great people there. And so I guess you could say like a free body diagram, and what I'm thinking when I immediately think of a free body diagram is I think of like a box. Oh, that's a horrible box. On a ramp, and we'll get into forces soon, but this is just an example. So this would be gravity. This would be normal force. And then, you know, this is the direction of the force, and you have a force applied, like right here, blah, blah, blah. There's a person right here and he's pushing this box. Whatever. This is like a free body diagram. You're drawing this. You're drawing what the problem is asking, or what you think the problem says. Okay, we have this car and it's going here, and there's this guy in the weird balloons. Like, okay, let's draw this out. Let's take these thoughts in our brain and put them out on paper. Cool. That was a way overly described free body diagram. Sure, cool. That's the simple sketch. You'll also need to decide which direction is positive and which direction is negative, or which direction is at the 0 point. Make sure that is crucial, especially when you're solving problems for acceleration. You know, we already saw the XY plot. We had negative acceleration. We had the big magnitude. We had a little magnitude. They were both negative acceleration. definitely need to write that down for sure. Finding the correct equation is also essential. You will have lots of equations, and these are called kinematic equations. Some of these, yeah, so right here, you'll have kinematic equations, and you'll need to put them basically in braces, and I write them down no matter if I use it or not, and then I circle which equations I use in that problem, but I always write down all 4 kinematic equations on every problem, and I circle which ones I'm going to be using. So you need to figure out and find which values you're looking for and which values you already have. I call that bookkeeping. And you just write it down. You write, oh, V initial equals 0 meters per second. Great. T0 equals 0. Okay, write this down. What am I looking for? What am I missing? You know. So those are 2 important things. What am I looking for versus what am I missing? You might need to calculate a couple times. You might need to find the missing values before you actually find the final answer. Make a list of what is given. That's what I just said. You make a list. I call it bookkeeping. Put all of it on, I always put it on the left side of the paper. List what you have and what you're missing and what you need to solve. That all needs to go on the right in very organized sense. The rest of the paper will be used for your free body diagram at the top and then your calculations at the bottom. This just is, I mean, I'm not really much for structure. I'm very like blah, but this is crucial because it will help you solve these equations. Particularly if you have ADHD like me, you're going to need every type of organization skill you can use. This will definitely help you. Identify exactly what needs to be determined in the problem. So identify the unknowns, identify the knowns, you already did. Find an set of equations to help you solve the problem. I write them all out, and then I just circle which ones I think I'm gonna need and use, and then you know, solve for whatever I need at the moment, which I hope you know how to solve for things and like rearrange equations. I hope you know how to do that. Substitute in the knowns, sure, with their appropriate units, guys. Don't forget units. I saw a lot of people's work that didn't, they like wrote out numbers and they didn't put units. Make sure you put those units on every single number, because I guarantee you, you're gonna get some questions wrong if you forget units, because you're gonna forget. It's very important. Cool. Check to see if the answer is reasonable. The very first lab, I had people say, oh, my heart beats 60 times per 1 second. If your heart beats 60 times in 1 second, does that seem reasonable to you? I hope not, because you'd probably be lying on the floor dying, which would be awful, and yeah, you probably wouldn't finish your lab report, which would suck. Yeah, so check to make sure. If that guy who was speeding up is going 1,000,000 miles per hour or something, and you convert that into meters per second, and like, I mean, make sure these values make sense. You know, a meter is this long. If it's going 50 meters per second, 50 of these meters, do you think that's like reasonable? Just kind of common sense it. Common sense, yeah. Unreasonable results, yeah, you can read this, blah, 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 read it. Yeah, read it on your own time. This is in the textbook, very important. This is 2.6 in the kinematics, chapter 2 section. Cool, great, we got that. Where am I going? Okay. Questions now. Okay. Sorry, I love the Grand Tour. If you don't have Amazon Prime and you haven't seen the Grand Tour, get Amazon Prime and then go see the Grand Tour. It's great. It's 3 old white British dudes and they're just so ridiculous. Like, it's bad. It's just, they're so old. It's just really funny. It reminds me of my dad. Okay. First question, number 1 question. I didn't put number 1, 2, and 3. Whoops. Okay. This question right here. When a car speeds up, acceleration is A, negative, B, positive, or C, 0 meters per second squared. So when a car speeds up, What is the acceleration? Top Gear. Oh yeah, Top Gear is like I love that show. I think I kind of like the Grand Tour better because they have a lot more money to do a lot more things, and I like that. Everybody participate. Everybody participate. You can go ahead and voice it out if you want to. That's okay. Just voice it out. Awesome. Perfect. Yes. A car speeds up the acceleration. Think about the XY plot that we were plotting before. It's speeding up. It's in the positive X direction. Sure. If you're a rocket, let's just say my parents live 40 minutes from Cape Canaveral. They do. I would watch rocket launches all the time. It was honestly the coolest thing. And if you didn't watch them, you heard them, you felt them. Like they would like gyrate your chest. Like you would be like, ah! Like it was crazy. You could feel it. In that sense, it would be accelerating in the what direction? A rocket. Well, what direction? Remember, think about this plot, this XY plot. So definitely positive, yep. The right? I mean, sure. The answer I was looking for was the positive Y direction. Absolutely. None of you may not be old enough to remember the Challenger. Maybe you do, maybe you were very small. But the Challenger went up and then it kind of went back down and crashed and exploded and yeah, so that was really sad. That would technically be in the what direction? If it went up and then, let's just say it didn't explode and went back down. Negative Y direction, yes. Good. Negative Y direction. You could say, I mean, yeah, negative Y, for sure. Great job. When a car slows down, acceleration is? When that guy in the blue car or in the green car saw that dude with the balloons, what was the direction of the acceleration? Yep, it was negative. Good job. A car is going at a constant 100 kilometers per hour. 100 kilometers. I think if you're going 60 miles an hour, you're going 100 kilometers per hour. So let's just say you're going 60 down the highway, 95, you'd be going very slow. I would probably honk at you and move. But if you're going 60 miles an hour on 95, you would technically be going 100 kilometers per hour. Am I right by that? I think that's what that is. Or it's either like you're going 100 miles per hour and you're actually, no, I think it's going 100 miles or 60 miles per hour would actually be exactly 100 kilometers per hour. Okay, a car is going that velocity. We know it's a velocity because it's not hours squared, right? There's kilometers per hour. Constant velocity. What is that acceleration? Let's see what you guys get. Oh man, everybody's texting me. Okay, sorry, I had to check my mom back.
So Professor Smith,
Mm-hmm.
This question is kind of confusing because if the car is going constant at 100 kilometers per hour, you would automatically think that it is like acceleration is a change in the velocity, and the velocity is not changing. So then, okay, got it.
Yeah, exactly. Yeah, exactly. And if you have to like say that out loud to make it kind of connect, do it. I mean, talk to yourself, talk to your wall. This is why I always like to say, like, physics is such a collaborative, really, it's a very collaborative, what's the word? Genre. Physics is a very collaborative genre. You have to, especially for ADHD people, you have to like, I mean, saying it out loud is gonna like, oh, yeah, wait, oh, yeah. So if you have to do it, yeah, talking out loud helps. If you got to talk to a parent, you got to talk to your little sister and say, hey, this is this, listen to me. Okay, bye. And then that, like, that's whatever, you know, just annoy your siblings, whatever, do it. Because they probably annoy you. Yeah, do it. I mean, so that's great. Yeah, absolutely. It's not really positive. So think about this XY graph yet again. Think about this XY plot. And you're going at a constant velocity. This XY plot is an acceleration plot. You're going to constant velocity. You're at the 0 point right here. Your acceleration is 0. Great job. Awesome. Very good. No acceleration. You are absolutely correct. Okay, things to know for lab 3. We're getting into lab 3. Who has not looked at lab 3? We'll go ahead and look at that if you haven't. I love this stuff. Lab 3. Oh, also, quick question. Have you guys kind of gotten used to Firefox yet? Is it kind of more clear on how to use it? How is that going? Like how is Firefox working for you guys?
I've only used the Firefox like the timer and the one that we use, like the latitude longitude one. I haven't used anything else on it. So
yeah, same.
Okay, cool. And how did that work for you guys? Was that kind of straightforward, or was that like super confusing?
So
sorry.
Go ahead.
I was just gonna say it was straightforward because you told us which one to use.
Okay.
Like you told us to use what was it, like the GPS something.
Yeah.
Like the first week I didn't know which one to choose, but because you told us, I was like, oh, okay.
Okay, cool. Yeah. So the first week's lab, I was kind of testing how independent you guys were, and how much I needed to elaborate on things. Which is why I kind of was thinking, you know what, if people don't do very well on this could be their dropped lab, because honestly, the rest of the labs are going to be way less stuff. There's going to be way less stuff to do on the rest of the labs than the first lab. So that was a good tester. And we had a lot of confusion, sure. So I'm glad that explaining this, where to go, where to see that, what each little tab does, like graph and absolute, and there's like something else, and simple, and this pause button right here, and then you have to use those 3 little dots right there, and that's how you export data. And I recommended to people that asked me, I was like, I sent mine to Google Drive, my Google Drive, and then I made the plot, and I just opened up Excel and made my plot from there. So, sure. Awesome. Glad to hear. Like I said, if you have absolutely any question, whether you think it's stupid or not, it's not stupid when it pertains to physics and doing something. I mean, I might be a little like, oh, come on, you can figure this out. But, you know, honestly, if you have a question, I'm going to help you. Like, you know, it's confusing, especially, I think most of the people in this course, like 99% of them, you guys are young. So easier to figure out. I don't think there's anybody that's old in this course. Okay, yeah, that's good. Good, glad that works. Okay. We're gonna go ahead actually and look at the lab because I don't know if you have yet. We'll just go do that.
I've looked at it, but since I haven't started reading the chapter, like I kind of understand, but it also seems complicated at the same time.
Okay, cool. We'll go through it. All right. For each objective, please keep your data and screenshots together so that way I know which data goes with which objective. So basically what I'm saying is for objective 1, whatever data I ask for, keep it in that objective 1 part. So what I'm looking for here is, you know how I say like, oh, if you have in your procedure, you'll write part 1's procedure and then you'll write part 2's procedure. And then you'll write part 1's data and observations and you write part 2 data and observations and then you know, same thing. Here, I don't really care what you do in terms of keep it organized, but I would say you can write the procedure. So do everything for each objective, I guess. For the conclusion, keep that as the conclusion for the whole lab. So
What
make
about
that
the-
the last paragraph.
What about the materials, since it's probably just going to be like our phone and a table?
There's going to be a phone. So everybody has a smartphone and everybody has a table. They have a surface. They have a flat surface that they can work on. Even if you have to go outside and use the sidewalk, that's a flat surface. Yeah. Ask smart people dumb questions. Huh. That's not a dumb question. I'm just like, I like that. I like that quote. Yes. Yeah. Oh, I really like it when people draw things. I like it. I like to see, like, even if they're stick figures or whatever, like I suck at drawing, but I just like to see like drawings and pictures of like, I mean, pictures of your sidewalk is like, I think that's just so cool. I'm like, oh, that's weird. It's just like their sidewalk that they see every day. Like, that's so cool, you know, because I don't get to see you guys in person. So it kind of sucks. It makes me sad. But anyway, I think that's kind of cute when you add like little pictures and like drawings. I love that. Okay, anyway, moving on. Yeah, so objective 1 for part 1 of lab 3, constant acceleration. This lab was particularly taken, I edited it, from a group of people at the Lawrence Livermore lab. Basically a physics lab. They're just a bunch of physics nerds. But they were like, oh, wow, the way physics is written now, it's just so like exclusive. Like it's so exclusive. It's like they don't want, if you're not good at physics, you can't do this stuff. Well, they were like, no, it's not very nice. Like physics, as I said, people say I'm smart. They say like, oh, you're a genius. I'm like, no, I'm not. I just really had a passion for it. And I studied my literal ass off to understand physics. You can get it. You will get it. So this is written with that in mind. Simple. So what you're going to do for objective 1 and for most of the objectives is, my mommy texted me back. Okay. Open your lab or your lab app, Firefox. You're going to find acceleration without G in Firefox. That's the very first one right at the top. Super simple. You're going to move your phone in quick, simple movements directed along the 3 axes of your phone. Observe how the sensor in your phone reacts to this motion by observing the graphs or the X, Y, and Z plot. So now it's Y, X, and now there's a Z pointing out like this. And if I had 3 arms, I'd be able to make the Z. So this is Z, and this is X, and then this is Y. Yeah, it's weird. So we're gonna go back here, and this little diagram right here, the X, the X, the Y, and the Z. So Y is going vertical, cool. X is going like this. So we went up and down, and we went side to side. Z is like this. Ooh, woo, woo. Okay. Up and down. That's Y. This is X, and this is Z. Cool. Specifically, you're going to do single movement. So you're not going to go like this. Ooh. it's just gonna be, oh, I guess you can, I don't know, it's kind of up to you if you want to have that 0 point, if you want to have a 0 point where you started on. I probably would do that. And you're gonna go like this. That's a single movement, technically. Well, I guess.
So we move it both positive and negative of each direction.
Yes. Yes, that would be preferable. That would definitely be preferable. Oh, I stopped sharing my screen. 1 second. I need to go back and share that. Okay, why is this not working? Ugh. Okay, sure. Move in quick, simple movements along. Okay, so observe how the sensor reacts by the motion. Okay, great. I think that might be for number 2. Anyway, you're gonna have to do that at some point. There's a simple movement, and then there's one where you're like moving it. Move the phone in quick, simple movements directed along the 3 axes of your phone. So we already know what the 3 axes are. Great. Up and down, and X, Y, and Z. Observe how the sensor reacts to the motion by observing the graphs. You'll have the graphs right there. Easy peasy. Draw a diagram of your phone if you want. You can also take a picture of it and then just draw the arrows, whatever you want to do. And label them. Make sure you label everything. Please label everything. Now don't label stupid things. Like I of course know that this is your phone, but make sure you label the axes because this is something that can change based on the person. Make sure you include those positive and negative directions. Yeah. Sure. So that's objective 1. Make quick, simple movements. Cool. Like probably like this. Yeah. But do one at a time. So don't go like X positive and then Z and then Y. Like make sure you do this, do that, do that. As time goes on, you'll see how it works. I'll go back to the PowerPoint. You'll see like over time, you did this for X and then time goes on and then you did this for Y, sure. Okay, objective 2, investigate the acceleration of a table following a collision with your hand. Set your phone on a table. I'll move my camera a little bit down. Okay, I hope you can see. Okay, cool. My phone's on the table. Record the response of the 3 accelerometers to a soft knock on the table. Now I have a neoprene pad and it covers my whole desk. Well, most of it. Don't do that. That will dampen your vibration of your hand. So I want to make sure it's preferably on a table. If you have to do it on a sidewalk, you have to do what you have to do, but make sure you note that in your procedure or wherever. Make sure that's noted. So that way, if I look at your data and I'm like, whoa, this is crazy. It's understandable because you said, oh, it's on a sidewalk. Okay, great. Now we figured that out. I'm sure you have a table at home. Or clean off your dirty kitchen table and then move the stuff. Do a soft knock. Take a screenshot of that data. So like press the pause button, screenshot it, export the data. Or no, don't export it. Wait, 1 sec, don't export it. Just include that in your report. Expand the axes on Firefox. You can do this by, okay, I went to the acceleration without G. Press the pause button, which is actually the play button. Okay, I'm just doing this, whatever. Great, pause it. Expand the axes. So I think there's little arrows right there, which expand the axes. I think that's what. Okay, this one doesn't have, you can't move it. Oh, here's a graph of all of them together, which is cool. And you can also see the values on this simple tab. So there's like tabs up here. Let's go back. Oh. Let's go back to the first tab. Oh, and I screwed it up. Yeah, so I think what it means is just, oh, also on your reports, whenever you take a screenshot, don't like widen it and make it all weird and like stretch it onto your document. don't do that. Like, I can't read it. If it's like, if all the things are stretched, like keep it in this. If you need to make it bigger or make it smaller, use the corner. Like there's a corner, like this picture. So let's say this is your screenshot. Use the corner to make it bigger, but keeping it in the same proportions like I'm currently doing right now. Don't stretch it like this. Okay, because when you stretch it like that, that looks real gross. It just looks awful. Like, would you, like, don't do that. If you need to make it bigger, go like this in the corner, you know? This is gonna bother me. Okay, cool, it's back to its normal. Okay, don't do that. I'm a real pet peeve with that. It's like, come on, make it look pretty, you know? What do you end up? Okay, good. Explain the details of your observation, including 1, relative magnitudes of the x, y, z in acceleration. 2, the patterns that you observed. There will be a pattern. Just explain it. And if you don't know how to explain it, just text me and I will look at your data, look at your screenshot and be like, blah, 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 blah. Okay. And number 3, the initial sign of the acceleration following the impact. Was it negative? Was it positive? Let me know. May want to consider on the table. Great. Okay. Objective 3, explore the sensitivity of the accelerometer. Set your phone on the table, collect data for 10 seconds while your phone is at rest on the table. Let it rest. Let it sit here for 10 seconds. Let it go. And then carefully pick up your phone. Very carefully. Trying to minimize the acceleration and hold it there for 10 seconds. If you want to like see how my like elbow is like against the table to stabilize? You can do that too. I'll be okay with that. Just try to minimize that and then record that for 10 seconds. Then you just go and press stop. Now there's going to be some weird graph numbers that you have when you go to press stop. So just take those away. Just say that that's what happened when I pressed stop. Cool. Evaluate the average peak-to-peak acceleration on a plot, on a graph. So let's just say, has anyone ever seen a heart monitor that has like, it graphs your heart rate or your heart? It looks like this, okay? For those that don't know, it's like, you know, like that, like something like this, okay? Peak to peak. This is a peak right here. And this is a peak. And there will be a plot right here, and it'll have, this will be t, and this will be, you know, the acceleration. This is peak to peak, these peaks. Evaluate the average peak-to-peak acceleration, average. So not just at one instance, but averaging all of the peak-to-peak accelerations. So you have to have a peak-to-peak from right here and calculate the peak-to-peak right there, and then the peak-to-peaks over here, blah, 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 average them out. Evaluate the average peak-to-peak acceleration that we did it for the 2 conditions. Two conditions were what? What were the 2 conditions? And if you don't know, that's okay.
The phone sitting on the table and you holding the phone?
Yes, exactly. First condition, the phone sits on your table for 10 seconds. Cool. Second, your phone, you're holding it for 10 seconds. Those are the 2 conditions. Awesome, great. You may do this analysis within the Firefox application or by exporting the data to a spreadsheet. I would do the exporting. If you don't have time, you can do it within the Firefox application. I don't know how to do that. I don't. I will research it if people do have problems, but it's also a good idea that you also research it. Just go to the Firefox website and the Germans will be very happy to help you. Paste those graphs in your report to support the values that you provide. Cool. I'm sure that's easy. So average peak-to-peak value when it was in your hand, give me a number. Average peak-to-peak value of acceleration when it was on the table. These peak-to-peak values, these average values, should be in the units of acceleration. Add those units Don't forget them. If there's a number there and you don't, if there's a number, if you have numbers anywhere in your report, they need to have units. Unless you're like, oh, step 1, I did this. Like, don't include those. Like, let's be smart. You know, use your common sense. If there's a number there and it needs to have units, put them units in there. Okay, awesome. Number 4. Yeah.
I have a question. So I just want to clarify with the previous thing you said. So we're just finding the distance between the peaks of the graphs, and then what if it's like slanted? Do we just find the slope? Okay.
Yeah, so I'm gonna need to learn how, oh shoot. I did something wrong. Okay. Blah, 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 okay, blah, 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 blah. Okay, yeah, whatever. Peak to peak application, find the peak to peak. So basically you're gonna say, okay, at t equals 1 second, almost on the dot. At t equals 1 second, almost on the dot. Okay, you can kind of see that from right there. It's almost on the dot of 1 second. I'm looking at the x direction acceleration. You can say, okay, the peak, oh, I'm sorry, I was looking at y. Let's look at x. So probably use your best estimate to figure out what time it was. So 1.25, let's just say. And then you're gonna look at, you're gonna look at t equals 0.25. And then the next peak as it is at t equals 0.5. So I'm dividing them in quarters, which is kind of how it is. If you want to, it honestly depends on where your peaks are. You need to determine the difference between those. So like take the average of, or we'll find the, of course, find the peak to peak, and then take all of the averages. And if you want to, you can only do like one set. But honestly, hopefully you're gonna get data that's very small. So you're gonna need to be able to zoom in and really look at it. So here's what you can do is you can zoom in and really get, using your 2 fingers, really get that exact data and determine what's this. So at 1 point, oh, I was close. 1.20, maybe like 1.19. That's
There's a button, there should be a button that says like pick data. And you click that and you can just like move your hand along each line. Like when you're in.
Oh, I see that. Yeah. There's like a middle part right there. Yep, yeah. You're right. Pick data. It will tell you. Oh, it's all white. See, it'll tell you this information, which you need to do the report. Yeah, what's up?
I said that's just cool.
Oh yeah, I know. This like phone app is like freaking awesome. Like, I mean, honestly, what do we need physics instruments for that are like multi-million-dollar physics instruments? Like, come on, we just use our phones. What? Okay, moving along.
I am curious, was that data that you just showed us, was that from like setting your phone on the table and then picking it up?
No, that was just from me moving it. But okay, I wanted to make it big enough to where you can see. Like I wanted to make sure that, you know, this isn't what your data should look like. But
okay,
just to stress how like this is what you need to do, I kind of did that just so I knew it would be big and be bigger.
For I just kind of quickly did the let it sit on a table and then pick it up, and it's just like a lot of tiny like squiggles, and then all of a sudden you get the big squiggles.
Yeah, of course. Yeah.
So sure. How do you do peak to peak for like
the little? You got to zoom in really big. You got to really zoom in to get that peak, to get those.
We have to take, so it's like within the course of 2 seconds, it's probably, oh Lord, like maybe 50 peaks. Do I have to do the average of all of those?
No, but probably do at least, I mean, if there's a lot of, so it's based on kind of your own judgment. Like, I mean, don't do the average of 2 or 3 peaks. I mean, that's way too little data. That will not give you a very good average. It should be this, especially when it's sitting on the table, you should get a very, you know, almost flat acceleration. If you don't have any peaks at all, just you might need to text me. We might need to do this. I might need to have like a Zoom call. Oh, I'm probably going to do a Zoom like live tutoring session on Friday this week. So if you have any questions and you're doing the lab at the same time, like you can totally do that. You can do the lab and sit here and do it in front of Zoom. And if you have any live questions, I'll be here. So Friday, I'm going to do that since we started, later this week. Be here on Friday. I'll probably do it Friday evening, just so I know that everybody's kind of home. Maybe, I don't know whether you guys work at Friday nights. I can't be here for everybody, of course, but I feel like most people work during the day. Find that peak to peak on the table, find the peak to peak on the hand. If you have any like detailed questions about it when it's on the table, let me know. It should be very hard to do when it's on the table. When it's in your hand, you're gonna have some uneasy movements. Just find those. Cool. Objective 4, determine the maximum acceleration that can be measured by your sensor. You need to come up with a thing to do this. This is your kind of creativity here. What can you do to find the maximum acceleration measured by the sensor? It's going to be fun. And here's where we'll get into this. How does your phone's sensor work? This is just extra stuff that, doesn't need to be here for the lab, but it's really cool to know. So MEMS accelerometer, it's a micro electromechanical system accelerometer. So basically you have these, you have these 4 points right here with the circle and the slash in it. Those are fixed points. Those are called anchors. And this is legit in your phone right now. Like, it's so cool. This is how they measure GPS. This is how on Waze they measure how fast you're going with respect to not moving. These blue things will move. So these 4 corners are fixed, but this blue part right here is a flexible material, and it moves back and forth. Like this whole thing, this whole blue part moves back and forth. These green L's are fixed as well. They don't move, but they're sensing. So this is a very tiny space. I mean, this is what it looks like live right here. This is done by an electron microscope, or it's like micrometers big. Like, it's incredibly tiny. Your eyeballs cannot see this. They cannot see this right here. Your eyeballs cannot if you were to open your phone. So don't try it. But they can sense, because this is such a tiny space. These green things can sense when this blue thing is moving in between these 2 fixed points. It's really crazy. It's so cool. Yep, this is a movable seismic mass. You can measure earthquakes with your phone. Totally happened. The guys that did this at the Lawrence Livermore lab totally did this with their phones, and they have Firefox data to prove it. It's weird, really cool. Yeah, so this is just the math for this. So this is no acceleration, it stays in the middle. When it accelerates, that blue thing, like I said, moves, and it moves to either one or the other, depending on which direction you're going, which acceleration, negative or positive. So it's really cool. I have smartwatch, iPhone, Apple Watch. Great. Same stuff that's in your phone is in here. And look how tiny this thing is. I mean, this is so tiny compared to my big iPhone Max, X Max, whatever. It's really cool. Yet again, you see that these 4 fixed anchors, and you have this flexible material here, and it moves back and forth based on the acceleration. This is how your watch knows when you're exercising. It's really cool. These are also fixed points. Awesome. It's so cool. Okay, questions or comments? Do you have any questions? Reasonable questions, even if it's not reasonable and you ask me what I had for breakfast, whatever. Comments. I know we went over time. I'm so sorry.
For the 4th part where you said, try to figure out the limit of your thing, do we have to have it in hand? Like, can it be in our pocket?
Yes, it has to stay in your hand.
All right.
Well, you know what? If you find a cool way to do it, it shouldn't leave your body area. Okay? So if you want to keep it like on your booty, you can do that. I'll say, yeah, that's cool. Just make sure you note that in your report. Make sure you note that, so that way I know. I'm sorry. Okay. Explain what you did. Just explain what you did. How did you find the maximum acceleration that your human body can give to this phone? And then you need to find that value. What's the maximum value? And it should be the maximum value on the plot, you know? Just give me that. That would be great. Anything else? Anything that you're kind of confused on? Just answer these questions. You may consider knocking on the table. So in part 2, or in objective 2, you can knock on different parts of the tables. If you want to put that, like all of the possibilities that you did in your report, go ahead. If not, whatever. But just, I want to see stuff. Anything? Yes. Oh, there's 2. I'm sorry. I didn't have my chat box up and it's gone now.
I'm still a little
Yes.
confused about finding the average acceleration from the peaks.
Okay.
Like, what do you mean by that?
So, peak to peak acceleration. Basically, it gives it to you, and Mary made a great point. It will give you this data. So if you see here,
Okay.
let me, hold on, sorry. It's a little blurry, I'm so sorry. That works. Okay, so do you see, it's a 6 point blah, blah, blah,
Mhm.
meters per second squared. So that will give you the acceleration at that point in time. Now, if you go to the other, so if you have to be on pick data, because I was going to make you do it the hard way and that would have been not very fun. So from here, from here to here, so these 2 points. So the first one was 6 point blah, 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 whatever. This one is 5 point blah, 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 whatever, meters per second squared.
Mhm.
You're going to mark that down, mark 0.1, 0.2, 0.3, 0.4, because there's four possible points in this first section here. You can find the average of just this section, or you can find the average, preferably, of the whole thing. Just make sure to basically take the average of these values, add them all up, and then divide them by how many peaks there were.
Okay. I didn't know that they gave you the actual acceleration at that point. I thought it was like just the time or something.
Yeah, and I was gonna, because I'm glad that Mary said something, because I probably would have sent out an announcement, because I usually do the labs with you guys. I just don't like write my own report. I don't need to. But I probably would have been like, oh my God, there's this thing and it's awesome, and you don't have to do any actual like crazy work. You could just pick that data. Yeah, so great question, great question. Yeah, does that kind of help you a little bit more?
No, that makes a lot more sense. Thank you.
Okay, cool, awesome, awesome. Any more questions like that? Or any other questions at all?
I do have a question. Since we're doing 4 parts, like we're doing the like every step of the lab report for like all 4 parts, is it okay if, like, obviously we want to be detailed and like so you know what we're doing, but is it okay if we aren't like as super detailed as we were like the past 2 labs?
Yeah, you don't have to be super detailed. Really, I'm looking for, it'll probably be the average about, with pictures, probably 4 pages. I mean, some people would go above and beyond the detail. I mean, their pages, they have like 18 pages. And I'm like, whoa, bro, dude, don't spend that much time on a lab. Like, oh my God, calm down. Like, I don't want to read this either. Like, don't give me 18 pages. Come on. You know, 4 or 5 pages. If it's 3 pages and you have all the things you need, yeah, that's totally fine.
And then the material section, can that just all be like all 4 parts have the same materials, since it's basically going to be like a phone in a table?
Yeah, so go ahead, like the very first part of your research paper, just write down all the materials you use. Don't put materials for each objective. Just write down all the materials, yeah. And then so really what I'm only looking for is do you the procedure and the error analysis and the data and observations for each. So that'll be 3 things for each objective. The conclusion you want to make at the very end and conclude about the whole thing. You don't have to write a conclusion for each one. Yeah. Particularly looking for error analysis. If you, I'm also looking for how well do you do sig figs. Actually, no, I'm not really looking for that. But if you do sig figs, awesome. I like that. That's good. It'd be so much easier if I could, like, if you guys were in groups and I could just go around to each table and you guys would do this in front of me and I'd just be like, oh yeah, look at these sig figs. But it's really hard to do without, I mean, everybody's doing their own thing. So I really kind of don't want to take the time to redo every single person's math and check for their sig figs. Like, that's a lot of time. Any other questions?
I do have a general question about sig figs. I was noticing when I was doing my lab last time that I would use like the calculator or Excel to like calculate things, and the sig figs for the answer would be significantly less than the sig figs for the two inputs. Like I would have like 10 significant figures for latitude, but then like it would be like 0.00003. So it's only
That,
one.
yeah, so that definitely did happen on a couple people's. So, you know, with that, that's really weird. So if it's 0.0000, those are actually like placeholders. Like those are things you, or those are, well, no, they're,
Because from the text it was saying only the number 3 would be a significant figure because the rest are just placeholders.
yes.
If it was 0.000300, those last two zeros.
Yes, so the last two zeros are important. They are significant. They are significant figures. So yeah, so really if you get a number that's like 0.000000, that's a zero. That's a zero. Oh my God. That's a zero. Okay. And it's like 2, 5. So technically how you would really, should be 0. How you really do it is, let's say you had 3 sig figs, okay? But you only have 2 digits right here. What this really should be, what you need to do here is 2.5 times 10 to the blah, blah, blah. But let's say you need 3 sig figs. So you should do 2.50 times 10 to the blah, 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 whatever. Let's see. 1, 2, 3, 4, 5, 6 to the -6.
Are we allowed to put the 0 after the 2.5? Because from the way they were explaining uncertainties, like you're not allowed to say you have 2.50 unless you're confident you have 2.50. Whereas
Yeah, so
if it gives us 0.000025, you're only confident it has 25.
25009. This would be technically 0002501. But you only need 3 sig figs, so you really don't need that one. So if you did have a big, big long number like that, I mean, technically.
What if the calculator doesn't give you, like
So that's also another issue. You know, that's something you need to explain for sure. Like well, it's hard to explain when you have a multiple choice homework question for sure. I mean, I'd honestly talk to Dr. Diamond if you have like a specific issue, like a particular problem that you're working out, and it's really weird, I'd ask him. But generally, this is kind of like the general blah, blah, for sig figs, the stuff you need to do. This is what I personally would do. I'd say like, oh yeah, so technically you have 4 sig fig or four figures here. You have to kind of conclude at what's the significant figure. If the lowest number you have is 3, you have 3 sig figs, then you need to put down 3 sig figs. It shouldn't be 2.5 because that's only 2 sig figs. I don't know. Does that kind of help a little bit? It's a little weird.
No, I get it. I just, because with like, yeah, with the last lab, with the change in latitude was like, if it was like just so small, it would give me like for a latitude and longitude that each had 10 sig figs, I would get like 1 or 2 sig fig answers.
Right, exactly. Yeah, so that was super weird. Honestly, I don't really care because if they're just, I mean, if a number that tiny, you know, if you have 0.5 zeros in a number, I'm not going to be super picky about that. When you get into upper level physics, unfortunately, we don't really care when numbers are like extremely large or extremely small. Sig figs don't really have much meaning. We honestly, in astrophysics, we just do, like, if it's like 9 point blah, 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 we just say 10 times 10 to the blah, 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 or 1 times 10 to the blah, 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 like when the numbers become so large or so small. So astrophysics, the numbers are huge. In particle physics, the numbers are extremely small. That's why I'm not super caring about sig figs as much as Dr. Diamond is, and I should be, but I just don't care. I don't think it's significant to have significant figures in such detail and such like, ooh, I'm a stickler for this. Like, I don't care. Give me the numbers, show me all of your work, sure, show me all of those significant figures, you know, just to show me. But whatever your answer is, if you get 0.000000 and like 5 blah, 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 like just do it scientific notation, 2.5 times 10 to the blah. Put units, great, answer 100% A for that particular section, sure. Yeah. Anything else? Everybody's looks
I have a
pretty.
question for the error analysis. How can we quantify like the percent error we get from 5-ox, since it doesn't have the tick marks like a ruler does? Or like, you know what I mean?
So yes, I do know what you mean. Honestly, you don't need to calculate percent error. You can probably calculate uncertainty. So percent error, well, so error and uncertainty are basically the same, but percent error is a little different than uncertainty, because uncertainty would be like having this value right here, but instead it would be plus or minus 0.7. That would be uncertainty. But percent error is literally calculating percent error. So you'd have to do the percent error equation. So actual value minus experimental value over blah, blah, blah. You know, like you have to do that. That's percent error. For this, it's going to be okay just to calculate uncertainty. And you can also explain it. If you want to calculate percent error, by all means, go ahead. If it's wrong, I'm gonna be like, oh, that's wrong. But it's kind of up to you. I would definitely calculate uncertainty, because you'll always have uncertainty in anything. I'd like to see that more than percent error for sure. But if you want to calculate percent error, by all means, go ahead.